So that equals to probability the z less than equal to the absolute value of z less than equal to z alpha over 2. Okay, then we can both sides multiply by sigma over square root of n. So that's why this is what we get. And this guy is the maximum error bound. So let's define it to be E. So define E to be Z alpha over 2 times sigma over square root of n. Then this is the maximum error bound. So, well, what does that mean? Okay, let's say, suppose that we get a sample. The sample, we have maybe 20 numbers in that sample, and then the mean, let's say if the mean is 15, and then we get this maximum error bound is like 3. What does that mean? Well, then we are, let's say this is the maximum error bound is 3 with probability 0.95, okay? With probability 0.95, that means I'm 95% confident that my actual population mean will lie in the range of, so we know the x bar is 15, then this guy 15 minus 3 is 12, 15 plus 3 is 18, okay? So I'm 95% confident that my population mean will lie within this range from 12 to 18. Okay, so now we not only get an estimate 15, but we also have like a sense about how close my population mean will be close to the sample mean. Okay, so fact, the error absolute value of x bar minus mu will be at most E equals to Z alpha over 2 times sigma over square root of n, this maximum error bound with a probability of 1 minus alpha. So what are the common used values for 1 minus alpha? It's usually going to be 0.9, 0.95, and 0.99. Okay, so right now I'm going to draw the picture with you. Okay, so let's see. We draw the big one. Okay, and this one, this is Z, this is 0. Okay, so let's say this is 0.9. Okay, so this is 0.9. What does that mean? Okay, it means that this guy, remember if this guy is 0.9, then this guy and this guy together is 0.1, then one of this guy is 0.05, right? So this guy is 0.05. So far so good, everybody? And what's 0.05? Well, 0.05, that is, so how do we find 0.05? Okay, there's two ways we can find it. First way, if we use table 3, that is the CDI values for the standard normal distribution. Okay, to find 0.05 means we want to find a Z value such that the CDF of that Z value, think about it. Well, this is 0.05, then the area before, the area on the left hand side of that is 0.95. Okay, so we're looking for the Z value such that CDF for that is 0.95. Okay, so let's find our table. So we are looking for the probability which is close to 0.95. Can you see 0.95? Let's see, 0.94. So can you see this? We have 0.9495 and 0.9505. So that's why you can see 0.95 is exactly in the between of them. So that this guy corresponds to 1.6 4. So this is 1.64. This is 1.65. Then in the between, then it corresponds to 1.645. So that's why we know that Z, okay, from the table, we know Z 0.05 is 1.645. Okay, so this is 1.645. So far, so good, everybody. Okay, next. How about 0.95? Where 0.95, let's say this region is 0.95. Well, then each piece, both of them together is 0.05. Each of them is 0.025. Okay, Z 0.025. So we're looking for the Z value. So we're looking for the Z value such that phi of Z value is, see, this is 0.025, and then on the left it's going to be 1 minus 0.025, so 0.975. So we're looking for Z value such that the CDF is close to 0.975. 975. Which one is closest? Oh, we have this guy. So this guy corresponds to 1.96. Okay, so that's why we know this is 1.96. Okay, so this is 1.96. How about 0.99? Well, 0.99 is big, right? Let's say this is 0.99. Well, then each piece, okay, both of these together is 0.01. Then when we divide it by 2, we get 0.005. So far, so good. So how do we find that? Okay, 0.005. We're looking for the Z value such that if this is 0.005, then this is 0.995. Okay, so V of Z is 0.995. Let's look at our table. 0.995. Where is it? Which one is the closest? Oh, somewhere between them, right? So this guy is 2.5. What's that number? 2.57, and this is 2.58. Well, it's right at the middle of that. So I would say 2.575. So this is 2.575. Okay, does it make sense? You can see 2.575 is bigger than 1.96. It's bigger than 1.645. So that's why it matched with our graph. Okay, and actually there is another way to find those numbers is by table 4. Oh, you might say, isn't it? This is a t-distribution table? Yes. That is the t-distribution table, the last page of our table. Okay, we get values of t alpha. But do you remember when nu, the degree of freedom, goes to infinity, what do we get? We get t nu. When nu goes to infinity, we get the standard normal distribution. So the last row of our t table is actually z alpha values. So that's why Z alpha 0.05. Okay, so Z alpha 0.05, we get 1.645. Do we have the same answer? Yeah, 1.645. And then Z 0.025. Z 0.025, that is 1.96. See? It's the same. Okay, so we don't need to do the calculation of the CDF values. We can just read from the t table. And alpha, so Z 0.005, well, that's the last column, right? And what do we get? Do we get 2.576? Well, this is more accurate because we just look at our previous picture and then we say, oh, it's a number between 2.57 and 2.58. Okay, then we pick 2.575. But you can see the actual value is 2.576. It's still close, so that's okay. All right, so far so good, everybody. Okay, so yeah, table for the last row, okay, is the z alpha values. Okay, and then let's continue. Example 1. An engineer intends to use the mean of a random sample of size n equals to 150 to estimate the average mechanical aptitude of assembly line workers. On the basis of experience, the engineer assumed that sigma equals to 6.2. Wow, that is the population standard deviation. What can be asserted with probability 0.99 about the maximum size of this error? Okay, so let's see. Probability 0.99. So probability is always like 1 minus alpha. So 1 minus alpha is 0.99. Then what is alpha? Well, alpha is 1 minus 0.99, which is 0.01. Then alpha over 2 will be 0.005. So far, so good. And our n is 150. Our sigma equals 6.2. And then the problem is asking what can we say about the maximum size of error with probability 0.99. Well, the formula is z sub alpha over 2 times sigma over square root of n. That equals z 0.005 times sigma and then over square root of n. Okay, what's z 0.005? So we just talk about that. That is, let's use a t table value because that is more accurate. So 2.576. 2.576 times sigma is 6.2 and square root of n is 150. Okay, let's plug this in our calculator. And what do we get? So you can also try to practice putting in this number into your calculator. Okay. Square root of 150. Okay. So I got 1.30404. So 40. So far so good, everybody? Okay, what does that mean? Okay, it means the engineer can assert with probability 0.99 that his error will be at most 1.3040. Okay, so this is what he can assert. So far so good, everybody? So in general, we make probability statements about future values of random variable, and we make confidence statements once the data has been obtained. I.e., if the engineer has obtained a sample mean, which is 69.5, then we say the engineer can be 99% confident that the error of his estimate, 69.5, is about 1.304. So far, so good. So if something we haven't measured is for future values, we say, okay, we assert with probability 1 minus alpha. But if we already observed the data, we already obtained the data, then we talk about confidence. Okay, so we are like 1 minus alpha times 100% confidence that the error of the estimates is within that range. So far so good, everybody? Okay, next, determination of sample size. Suppose we want to estimate the population mean, and we want to assert with probability 1 minus alpha that the error will be at most some number prescribed quantity E. Then we can use the E formula to obtain the sample size we need. So here we're doing the opposite direction. Okay, so the previous we know the sample size, and then we find the error bound. Okay, right now we're given the error bound. We want to control our error bound within some number, and then we want to know what's the size of the sample, how many data we need to obtain so that our error bound is within that number. Okay, so let's solve for n. So this is our error bound formula. We solve for n. So we both sides multiply by square root of n, and both sides divided by e. So it's like you switch their position, right? Then we have square root of n here, and then e in the bottom. We can square both sides. When we square both sides, this is the formula of n we get. So far so good, everybody? Yeah, very easy. So example 2, a research worker wants to estimate the average time it takes the mechanic to rotate the tires of a car. She wants to be able to assert with 95% confidence that the mean of a sample is off by at most 0.5 minutes. If she can presume from past experience that the population standard deviation is 1.6 minutes, how large a sample will she have to take? Okay, so here, let's figure out the number. So 95% confidence, that's like 0.95. That is 1 minus alpha. Well then, what is alpha? Alpha is then 0.05, right? Alpha over 2 is 0.025. So far, so good, everybody? What is z? Alpha over 2, 0.025. Okay, so let's find our z table. 0.025 here, that is 1.96. So 1.96. Okay, so let's use our n formula. N equals so z alpha over 2 times sigma over, sorry, I say sigma, but I put down alpha. Okay. All right, so here, what is our E? E is at most, so E is less than or equal to 0.5. And then sigma is 1.6. Let's plug in those numbers. So z alpha over 2 is 1.96. Sigma is 1.6. E is 0.5 square. So far, so good. Oh, okay, so let's plug this in our calculator. 1.96 times 1.6 over 0.5 square. What do we get? I get 39.3. So the sample must be an integer. Let me ask you, do you pick 39? Do you pick 39? Oh, because 3, the next digit, is less than 5, right? So we should round down, right? Is it round up? So here we gotta be very, very careful, because your E is less than equal 0.05. Then your N it should be greater equal to this number. So that's why you should pick N is 40. Okay, you have to bigger equal to that number. So that's why we can say the research worker should take 40 sample. 40 mechanics. Okay. Yes. So far, so good. Everybody? That is example 2. Let's continue. Okay, we mark. If we don't know sigma, okay, I don't know why there's missing. If we don't know sigma, sigma is the population standard deviation. We can use sample standard deviation as, okay, to approximate it if n is large. And if we can assume the population is normal, we don't require to have a big sample size, okay? We can use t distribution, i.e. t, which is x bar, the sample mean minus population mean over s over square root of n, is a random variable having a t distribution with n minus 1 degrees of freedom. So here we don't need n is large. What is large means? You remember the t table? When we only have the degree of freedom up to 29. So I would say 30 is the boundary line. If it's less than 30, that's small. Bigger than 30, that's large. Large, you can use the standard normal distribution. You don't need the t distribution. Okay? So here we don't need n is large, but we need normal population. In order to use the t distribution, the population must be normal. So we require extra assumption about the population. Okay, if that happens, then we use the t distribution to calculate. Okay, so everything holds except we replace the z by the t. Okay, we just replace the z by the t, and then we have the maximum error is t alpha over 2 times s over square root of n for sigma unknown. Okay, so when sample mean and the population standard deviation are available, then we can assert with 1 minus alpha 100% confidence that the error made in using the sample mean to approximate the population mean is at most E. Okay, that is the error bound. Okay, so let's look at example 3. In 6 determination of the melting point of a tin, a chemist obtained a mean of 232.6 degrees Celsius with a standard deviation of 0.14 degrees Celsius. Assume the population is normal. If he uses this mean to estimate the actual melting point of a tin, what can he assert with 98% confidence about the maximum error? Okay, let's put down the numbers. Okay, 6. What is 6? Oh, that is n, right? The sample size. And then the mean, well, the mean of the sample, right? Even though it doesn't say the sample mean is within the sample, he gets the mean of that. So that means the sample mean. Okay, and the standard deviation, so that is the that's the sample standard deviation, S. Okay, so assume that the population is normal. If it uses mean to estimate the actual melting point, which is the population mean, what can he assert with 98% confidence? So that's 0.98, which is 1 minus alpha. Well, then alpha is 1 minus 0.98. That is 0.02, right? Okay. Then alpha over 2 is 0.01. All right. So then what is the maximum error? Is t alpha over 2 times sigma over square root of n. What is t alpha over 2? Well, let's figure that out. Here, we look at table 4. T alpha over 2 is 0.01. What is the degree of freedom? Is that 6? Is that equals to the population, the sample size n? 6? No, it is 5. Okay, the degree of freedom is and minus 1, which is 6 minus 1, which is 5. Be careful. This is actually a common error. Okay, so let's go to the t table. So n, the degree of freedom is 5. And t sub 0.01, where's 0.01? Here. So we get 3.365. So this is 3.365. Okay? All right, let's continue and plug it in. So 3.365 times sigma. Oh, we don't have sigmas. Remember, we have the S. S is sample standard deviation. Okay, so S is 0.14 and square root of n, square root of 6. So far, so good, everybody? Yes, put this in our calculator and then we'll get 0.19. So far, so good, everybody? Okay, so that's why we can say the chemist can assert with 98% confidence that the melting point obtained is off by at most 0.19. What's the degree? Celsius. Okay? Degree Celsius. So far, so good, everybody? Yes. So let's make a summary. Remember, we have 3 cases. First case, we have large sample and we know sigma. We know the population standard deviation. In that case, we use the standard normal distribution to calculate. Okay, and then the maximum error bound for it is z alpha over 2 times sigma over square root of n. Okay, let's not look at this yet because we will talk about that in the next session. Okay, 9.2. Second case, if we have large n and we don't know sigma. Well, if we don't know the population standard deviation, we can use the sample standard deviation S to estimate it. Okay? And then the maximum error bound, we still use Z, okay? And then this is S. So now you can see the difference between case 1 and case 2. Okay, case 3, we don't have a large sample. We have a small sample. How small? Small is like less than equal to 29, right? That is small. Okay, but we have normal population, so it can be small, but it has to be normal population. And then here we don't need to know the population standard deviation as well. Okay, we use the sample standard deviation to calculate. And always keep in mind the degree of freedom is n minus 1, is not n. That is the common error. So what's going to change? We replace the z by the t, and we still have the s, sample standard deviation. Okay? So that is the maximum error bounds. So far, so good, everybody? All right. I'll see you in next session. Bye.